After we have looked at reflection, we need to look at refraction. State and apply Snell's law. We have to define the refractive index in terms of the ratio of the speeds of the wave in the two media, and also in terms of the angles of incidence and refraction. It's also defined in terms of the ratio of the wavelengths. We have two media. We have air above and we have glass below, which is the blue block. The radiation comes in at a speed, slows down and changes direction. This is refraction. First we draw the normal. We define the angle of incidence and the angle of refraction. So the light passes from air to glass. It slows down. It bends towards the normal. Its wavelength gets shorter. The angle of incidence is greater than the angle of refraction. We define n, which is the refractive index of the medium. We find that since that angle of incidence is greater than the angle of refraction, also the sine of the angle of incidence divided by the sine of the angle of refraction will always be greater than 1. The sine of the angle of incidence divided by the sine of the angle of refraction is equal to n2 divided by n1. In other words, it's the refractive index of the second medium divided by the refractive index of the first medium. In other words, the refractive index of glass divided by the refractive index of air. This could be an example. The refractive index of air is 1.0, or vacuum is 1.0. The refractive index of glass is 1.52. The angle of incidence would have 45 degrees. What would the angle of refraction be? Well, the rule is the sine of the angle of incidence divided by the sine of the angle of refraction is equal to the ratio of the refractive indices. So the sine of 45 divided by the sine of theta is equal to 1.52 divided by 1. So we basically need to rearrange this to make sine of theta r the subject. So we basically flipped everything, move sine of 45 to the other side, and we should be able to find a value for theta. You'll get a value which is certainly less than 45 degrees, maybe 35 or 30 degrees. Sometimes the light goes in another direction, from a slow medium to fast, whereas before, going from fast to slow, it bent towards the normal. This time it will bend away from the normal, where the angle of refraction is greater than the angle of incidence. So we have to have a general rule, and it's basically the equation at the bottom, which is the refractive index of air times by the sine of the angle in air, whether it be incidence or refraction, is equal to the refractive index of water divided by of the angle in the water. If you use this, then let's look at refraction in one dimension, just going in a line. So we go from light, we'll show the wavelengths going in a fast medium going into a slower medium. So what you'll find is that the wavelength will get smaller. So the light is travelling down with a large wavelength, goes into the second medium, it slows down, and the wavelength will get shorter. What you will find is that the frequency will be unchanged. So the frequency 1 is equal to the frequency 2. And we know that V is equal to F lambda. So V divided by lambda for the first medium must be equal to V divided by lambda for the second medium. In other words, if the velocity is faster, the wavelength will be longer. And this is another way. The ratio of the velocities will also be equal to the ratio of the wavelengths. This will be also equal to the ratio of the refractive indices. But remember, we have V1 divided by V2 is equal to lambda 1 divided by lambda 2. This, however, is N2 divided by N1. So the ratio of the sines, 1 over 2, is equal to the ratio of velocities, 1 over 2, is equal to the ratio of the wavelengths, 1 over 2, which is the ratio of the refractive indices, 2 over 1. So the refractive index is the one that behave in quite the same as the other ways, as the other variables. Sometimes you get a question like this. You have to basically find out what is the ratio of the speeds. Well, you can't really, you're not expected to take a protractor into the exam and measure the angle. This is one solution. But remember that the ratio of the speeds is also the ratio of the wavelengths. So basically we find the ratio, the wavelength of one, we find the wavelength of the other, and we find the ratio, and this will also be equal to the ratio of the speeds. We need to define a refractive index in terms of the ratio of the speeds of the wave in the two media. So this is the equation that we have. Remember, V1 over V2, lambda 1 over lambda 2, sine of theta 1 over sine of theta 2, N2 by N1.